Welcome to this video on theoretical computer science. We will analyze the mathematical foundations of combinatorial logic, specifically focusing on the limitations of the S combinator and its non-Turing completeness. Our research overview covers 5 key areas: historical foundations, the combinator basis, Turing completeness, the proof of limitations, and finally, implications and applications in modern computing. We begin with Chapter 1, Historical Foundations. We trace the origins of combinatorial logic from Schonfinkel's 1920 presentation to the development of modern proof theory. In 1920, Moses Schonfinkel introduced combinators as building blocks of logic in Göttingen. This revolutionary achievement provided the first formalism for universal computation, predating Turing machines. Haskell Curry independently discovered combinators at Princeton in 1927, formalizing the system and coining the term combinatorial logic. His foundational work established the field's axiomatic structure. Chapter 2 explores the combinator basis. We will understand S, K, and I, the minimal primitives required for computation. The SKI combinator calculus uses 3 primitives: I for identity, K for constant functions, and S for application distribution. I is redundant, as the complete basis is SK. Combinatorial completeness means any computable function can be represented in the system. The SK basis achieves this, establishing its equivalence to lambda calculus and Turing machines, supporting the Church-Turing thesis. Chapter 3 focuses on Turing completeness and Barendrecht's theorem, detailing the fundamental requirements for universal computation. Barendrecht's theorem states that any Turing-complete combinatorial logic basis must contain both the application combinator S and the erasure combinator K. This proves that S alone is incomplete. Chapter 4 presents the proof of S combinator limitations, establishing 5 fundamental laws that prove its non-Turing completeness. The S limitation laws show that S cannot simulate the K combinator, lacks internal state, and cannot implement branching or universal detection. These limitations stem from S's inability to discard arguments. Core proofs confirm that S cannot simulate K or perform variable erasure because S reduction preserves argument structure. Therefore, by Barendrecht's theorem, S is Turing incomplete. Chapter 5 explores the implications and applications of these theoretical insights in functional programming practice. Combinatorial logic is practical in compiler design, utilized in languages like David Turner's SASL and the foundations of Haskell. Compilers translate lambda terms into combinator graphs for efficient reduction, minimizing variable overhead. Modern research uses combinators in proof assistants like Coq and for WebAssembly compilation. Understanding these limits is critical for compiler design and reveals the minimal models needed for universal computation. S combinator research highlights the elegant boundaries of computation. Barendrecht's theorem proves SK is the minimal basis for completeness, bridging 1920s mathematical logic with 21st century programming principles.